Hey, everybody. In this episode of the podcast, we are going to talk about Chapter 3, Developing an Algorithm. So, Chapter 3 is what I like to call a proof of concept chapter. You'll notice as you're going through it, reading and watching or listening along with these, is that there is really no balance of new content here to offer you. Instead, this is really a sampling of more of what you've already seen. What these overview chapters do, chapter 3 rather is an overview chapter. Chapter 6 is an overview chapter. Really, chapter 9 is kind of the same thing. What these do is provide you with more detail. They give you bigger, better examples of the really shallow ones that you've seen by giving you slightly less shallow examples that have several of the components that you've been looking at working with all stitched together. So we're going to see what that means here. We are also going to go over a couple of the examples from the chapter, but we are going to make them better. In the way that you saw the kind of very, very basic pseudocode that you saw happening in chapters 1 and 2, and the pseudocode that you saw in the pseudocode type and pseudocode style documents and videos, we can really do better. And really what we'll hope to show you is the need to have to do better, because the better your pseudocode is, the more closely the next implementation of your code in whatever runtime environment or as it's developed into a concrete sequential process, the better your pseudocode is, the better the next developer in the chain is going to be at actually following through with that. On page 19, we have just a little bit of a reminder at the very top there. Things to remember are when we are in the process of defining and answering the problem, some things we need to keep in mind are the following: the input, the outputs, and the process. So inputs, outputs, process. So in order for us to do that, there's some things we have to keep in mind. First and foremost, remember again that an input is a list of data, whatever that means, that we need to provide the algorithm with to solve a problem. So a question I'm going to ask you now, and I'm going to ask you throughout the course of the semester, is where is the source of this data and where does that come from? That's going to be important in order to build the most robust applications and processes here. Is the input something we are going to get directly from the user? Is the input going to be something that we get from an outside party, so some other piece of data? These are questions that it is best to know the answer to. Second is output. Output is whatever the list of outputs that are required and where it is that they go. So think about things like to your screen, to a paper, to a file, etc. Those could be outputs in the way of a system sound. So when you have a system that goes, and makes a system beep, beep, that's an output. Actually, outputs can be even things like the fan noise coming from your system. They can be things like when lights, like light bulbs, that's the word I'm trying to look for here. Traditional, good old-fashioned Edison-style light bulbs is actually a design cue. When they go out, they actually burst. They make that noise. That noise is supposed to actually let you know that the light bulb itself is unrecoverable. So that's actually a design consideration, an output that went into making a piece of glass and filament, if you can believe that. Finally, we have processing. Processing is the list of all the actions needed to produce the required result. So I will highlight what those are. Those are going to be different. Processes are not simply just a recapturing and a regurgitation of all of the steps you underwent. Think about processing in the way of what math did we do. That's especially here leading up to this chapter, that's really the processes we're looking for here is, were there maths? Did we have to undergo an additional process to make an output. Again, they are not simply just a reiteration of step after step after step. So here we go. This is our first solution algorithm, and it's located right here on page 20. Program 1, it states, a program is required to read 3 numbers and then add them together and print their total. That's it. That's all that's required. The text would have us say that the solution is this. So remember, the solution is, this is what we are submitting. This is what is going to be passed along to the next developer in the chain that allows them to do exactly what we wanted them to do. So read 3 numbers, add numbers together, and print total number. That's it. My question here is this really the sum and total of every step it is that we needed to undergo in order to get the user or the process to the desired end result? Now, I argue that no, it isn't. First, there's a couple of things that we do have to change. Remember, in order for us to have good pseudocode, essentially our actionable keywords, right, have to be in all uppercase. So read, add, and print, those absolutely positively should be in uppercase, because again, that lets the next developer in the chain know that irrespective of what the runtime compiled language is going to be, that this is the action I'm looking for. All caps here removes any of the ambiguity as to what it is that you were looking for in putting down this pseudocode. Other things that make this pseudocode complete, whereas the version in the text is not, remember that we do need the module name. We need to be able to type and talk at the same time. That's one thing. But certainly we need to let the user, or the next developer in the chain rather, know what it is that we are looking to do here. And we also need to know when it is that we're done doing what we need. So to make this the most complete, our module should look like this. Module, add 3 numbers, read 3 numbers. Remember, read, the keyword being in all caps. Add numbers together. Remember, this is a mathematical operation, and hopefully the next developer in the chain knows what math is. And finally, print total number. Remember, print primarily means that this is going to be outputted to a sheet of paper. Just something to keep in mind. So my question here is this good enough? Will this produce the kind of output it is that we are expecting to get? And I posit, so it's my guess, that this really isn't going to produce what it is that we're expecting. So here I am, pretending that I am the next developer in the chain. I have simply gone out and chosen a runtime environment that's C++. It doesn't need to be C++. I could have chosen JavaScript. It just so happened I had a C++ window open, and I am a path of least resistance kind of person, so I chose to develop the solution that we had just provided as C++. Now remember, the sum and total of the pseudocode we put together simply says, read 3 numbers, add 3 numbers, print the sum of those 3 numbers. And in C++, this is what that looks like. So here's my variables. Remember, variables are the temporary containers we are going to put data into. It doesn't matter, but this is the syntax for getting 3 numbers. This is the syntax in C++ for adding 3 numbers. And this here on line 14 is the syntax for printing 3 numbers. Here's the problem. This was easy enough. As the next developer in the chain, I look at that and go, yes, sir, you told me get 3 numbers, add 3 numbers, print 3 numbers. I'm getting paid as little as possible for this, so this is exactly what I'm going to produce. Get 3 numbers, add 3 numbers, print 3 numbers. when I run this, here's the problem. This portion of the window over here, the right-hand third of my window, is the output. This is doing exactly what I've told it to do. Now, if you're the next user in the chain, it is your job to be the one who provides us with 3 numbers to add together. Am I doing anything here to provide you with any indication of what it is that I'm expecting? No. I haven't done anything to let you know that I'm expecting numbers. I haven't done anything to let you know that I'm expecting whole numbers. I haven't done anything to let you know that I'm expecting to output the sum of those 3 numbers. I have to know, as the developer, what I need to do to enter 3 numbers. So I have to type 1, hit the spacebar, 2, hit the spacebar, 3, hit the spacebar. And when I hit enter, I kind of unceremoniously just get dumped out the output, 6. Now, this is not good user design. What's going to happen here if I use my pseudocode, and if that pseudocode is developed into a runtime language, this is what it's going to look like. And what I can tell you is the user experience is going to be terrible. The user is going to look at this and say, I don't know what's going on. It's clearly broken. The user is going to look at this and have to call they're going to have to call your company, and they're going to have to say, what in tarnation is going on here? Why is the program that I have paid you to develop, why is that not doing what I expect? And because I haven't provided pseudocode that is complete enough for the next developer in the chain to actually complete what it is we were looking for. So this is why I argue that we have to be better than the text even when it comes to putting our pseudocode together, and we are going to start that process right now. So let's start to develop a better solution for add 3 numbers. Now, I am over here again in Sublime Text. Again, there's no huge advantage here to using Sublime Text. The biggest advantage this provides me with right now is to provide line numbers. So later on we can talk about line number 1, line number 2, line number 3, so on and so forth. If you are developing this solution alongside of me and you do not have Sublime Text, you can go ahead and feel free to use Word or Notepad or TextEdit or Vim if you are on a Linux machine and you hate graphical user interfaces. Whatever you want to put this together for the time being is fine. Like I said in a previous video cast, I care at this point far less about the solution you are using. I care at this point far less about anything other than your understanding of what it is we are doing and why it is that we are doing it. So I have already spotted us here the module name and the end of that module. So this way, the next developer in the chain knows what it is that we are talking about doing. Now, I'm going to give myself a little bit of space here to work with. This is not something you have to do, but it's something I do right away because, as you have seen, my ability to type, highly suspect, and this just clears out the space so that I have the room I need to work. And as a matter of fact, this is already shifted 1 too far over, so I just highlighted the whole kit and caboodle there, held down Shift and hit the Command key, or the Tab rather key. So that's hold down Shift and Tab at the same time, and we are going to see that get indented. So one of the first things that we saw that was an issue in the previous example was that our user didn't necessarily know what it was that the program we created was aiming at doing. In order to prevent that this time around, we will have a display for the user. Remember, display goes to the output, so in our case, a computer screen, and it signifies to the next developer in the chain that we are creating a two-way communication here, and that they should be expecting some kind of interaction. So display. This program will take 3 whole numbers from the user, add them, and display their total. There is little doubt after reading that what it is that our program aims to do. So next, what we want to do is get an input from the user. But my suggestion to you here is don't just assume that the user is going to know, okay, they told me what the program is about, I know I have to enter a number. Rather, lead the user to a good interaction with your program by actually telling them what to do. So this time around, our display is going to say, please enter number 1. When we're asking them for number 1, they're going to enter that. So now we have to get number 1. So what this is going to do is create a transaction, right? We are going to ask for an input. We are going to get an input. That is good end user design. Now, to keep up with the good end user design there, what we want to do is keep this interaction going, right? So the next thing we want to do is, let's get these moved over to where they need to be. We want to display enter number 2, and we want to get number 2. You'll notice the variable names we have here, number 1, number 2, and number 3. You'll also notice that these are in camel case, so number is always lowercase, and the first letter of either 1, 2, or 3 is in uppercase. And with this little interaction that we have created here, we are making 3 small transactions, 3 small, easy to follow transactions. Enter number 1, get number 1. Enter number 2, get number 2. Enter number 3, get number 3. So there's no real confusion there on behalf of the user as to what it is that I'm expecting from them. Now, next, you will recall in the previous example, it simply said add 3 numbers. Like we saw in the pseudocode terms and style screencasts, that seems okay with easy math, right? If it's adding or subtracting. What happens if we're doing it with complex engineering mathematics? That's not good. So what we always want to do is actually show the next developer in the chain the full complete sequence that they're going to need mathematically to get our solution algorithm done properly. So sum equals number 1 plus number 2 plus number 3, and in so doing, we are actually showing the next developer in the chain everything they need in order to get that math done. Is a sum of 3 numbers that difficult? No. But is compound interest difficult? Yes. Treat them all the same and never make a mistake. I think that that's a much better, more thorough way to go about thinking about every development you'll do in pseudocode. Next, if you'll recall our previous example, it simply vomited out the number 6 as though the number 6 has meaning in and of itself. It doesn't. Now, we could arguably simply display the number 6, right? Because our very first display to the user up here said, this program will take 3 whole numbers from the user, add them, and display their total. So technically speaking, we might assume that the user remembers that. We might assume that the user is going to look for the sum, and we might assume that they'll get meaning from that. Might assume is an awfully dangerous thing in the development world because those assumptions come back to haunt you. Better yet is to actually make the display. So better yet is to, let's get that extra space out of there. Display the sum is, and you'll notice that that is inside of I will continuously say parentheses today, I apologize. That is inside of quotation marks. That means display exactly what I am telling you to display. Outside of the quotation marks is sum. You'll notice sum is our variable. That variable here on line 13 is where we stored the actual mathematical operation of adding number 1 plus number 2 plus number 3. So when we put this all together, this block of code here is going to produce a much more satisfying kind of an operation than the previous operation. So what we're going to do next is to actually look at what this piece of pseudocode is going to produce in a runtime compiled language. So here we go again. This time I have taken our better set of pseudocode instructions. I have taken the pseudocode instructions we see here from the most immediately previous example. And what I have done is I have implemented those pieces of pseudocode into C++. So that is what this main window, the center rather window here looks like. So there's only small deviations between the first book example from page 20 and the example we just walked through a moment ago with simple text. There's very, very small changes here. Those changes are as follows. I put the outputs that I wanted in the program, and that's it. I have put the outputs there to create small transactional interactions with the user, and I have created displays, so outputs that help the user know that we are being led to a successful conclusion of the program. So this time around, if I run the program, we'll notice, anytime now, we'll notice, this is what happens in a live environment. Sometimes things don't go exactly the right way. Perfect, here we go. You'll notice this program will take 3 whole numbers from the user, add them, and display their total. So please enter number 1. I'm just going to enter number 1, number 2, number 2, number 3, number 3. So I'm being led to a good interaction by stating what the program's intentions are. And here, the very last line, the sum is 6. The program is communicating to me that the work we did on those transactions is in fact leading to a successful conclusion. The difference here between our code is minimum. If we take a look at the total difference in lines of code between the book example and our example, we'll see just how far we can get with a little bit more specificity. So here we are looking again at the original, modified rather, original piece of code we have from the text. Remember that these are available on page 20 if you wanted to see everything side by side here we have the 3 lines of code that we developed using exactly what the text told us with really, really small modifications. Remember, the text had read, add, and print in all lowercase. And remember, that's what provided the next developer in the chain with a less than satisfactory implementation of the code that we wanted. And if we take that and we look at what it is that we were able to produce the second time around with a much more thorough implementation of our pseudocode, this is the total difference that we're seeing there. The module here, as the text would have you implement, is 3 lines of code. The module here, as I suggest you would implement it, is a total of 8 lines of code. We have a small 5-line addition here that makes all the difference in the world. Rather than, in the text example, leaving the next developer in the chain with a huge amount of leeway to either increase or decrease the quality of our program. That's really not what we're looking for. What we want to do is here. We want to provide the solution as it is that we want it implemented, line for line, word for word, the way we want it implemented. We want to maintain control over what our displays are going to be. We want to maintain control over what it is that we want our variable names to be. So this way, when we hand it off to the next developer in the chain, they're going to be able to take this and go, okay, and really in very, very short order, take our pseudocode here and develop it into whatever the runtime compile time language is going to be. That is a far better way of stitching together a complete solution in pseudocode.